combinations count the number of ways to choose R items from n distinct items, when the selected items have no order, ranking, or position. So how are combinations different than permutations? With permutations, order matters. With combinations, order does not matter. For example, suppose we have 5 people and we want to choose 3 of them to be on a pizza taste testing team. Here, we are not choosing a first place, second place, and third place. We are just choosing which 3 people of the 5 are going to be on the team. So if Joe, Joseph, and Joey are selected, that is the same team as Joey, Joe, and Joseph. Changing the order does not create a new team. This is one combination of 3 taste testers from the set of 5 people. Let's compare this to permutations. If we used 5p3, we would be counting all possible arrangements of 3 people chosen from the 5. The formula for permutations is nPr equals n factorial divided by the quantity n minus r factorial. 5p3 would be 5 factorial divided by the quantity 5 minus 3 factorial, which is equal to 5 factorial divided by 2 factorial. We write out the long form of the factorial, and we cancel out the 2 times 1, and we're left with 5 times 4 times 3, which equals 60. So there are 60 arrangements of 3 people from a set of 5 people. Now, how many unique subsets of 3 taste testers exist among all these arrangements? Well, Joe, Joseph, Joey is counted separately from Joe, Joey, Joseph. It is also counted separately from Joseph, Joe, and Joey, and from every other arrangement of the same 3 people. How many times does this one unique subset of 3 people get counted? Well, how many ways can we arrange a set of 3 people? The number of ways we can arrange 3 people is 3 factorial. That comes from just the definition of factorials, right? The number of ways we can arrange n items is n factorial. So the number of ways we can arrange 3 people is 3 factorial. And 3 factorial is equal to 3 times 2 times 1, which is equal to 6. Each unique subset of 3 people is being counted 6 times inside the permutation count. That means if we divide by 3 factorial, we essentially deduplicate all the potential orderings of the same subsets and are left with the unique number of ways we can select subsets of 3 from the starting 5 people. This gives us the combination formula. nCr is equal to n factorial divided by the product of r factorial times the quantity n minus r factorial. There are a few different ways people denote combinations, but nCr is one common way. Here, n is the total number of objects we are choosing from, and r is the number of objects we are choosing. This formula assumes the objects are distinct, selections are made without replacement, and 0 is less than or equal to r is less than or equal to n. Another way to think about it is nCr is equal to nPr divided by r factorial. We just start with the permutation count, nPr, which is the count of ordered arrangements, and then we divide by r factorial to remove the repeated arrangements of each unique subset. In our example, we have 5 people and we are choosing 3, so 5c3. Using the formula, we get 5 factorial divided by 3 factorial times a quantity 5 minus 3 factorial. That becomes 5 factorial divided by 3 factorial times 2 factorial. Writing this out, we have 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 2 times 1. The 3 factorial in the denominator is removing the repeated arrangements of each subset. The 2 factorial cancels the unused tail of the 5 factorial after accounting for the 3 selected positions. We can cancel out 3 times 2 times 1 and we're left with 5 times 4 divided by 2 times 1, which is 20 divided by 2, and that equals 10. There are 10 different subsets of 3 people we can make from 5 people. Let's look at one more quick example. Suppose we have 8 students, and we want to choose 2 of them to work together on a project. Since there is no first position or second position, order does not matter here. Alex and Jordan is the same group as Jordan and Alex. So here we are working with combinations. We have a total of 8 people and we're choosing 2 of them, so we write this as 8c2. Using the formula, we get 8 factorial divided by 2 factorial times the quantity 8 minus 2 factorial. which is 8 factorial divided by 2 factorial times 6 factorial. The 6 factorial cancels the unused tail of 8 factorial, leaving 8 times 7 over 2 factorial. So we get 56 divided by 2, which is 28. There are 28 different subsets of 2 students we can choose from a pool of 8 students. The big idea is this: permutations count arrangements and combinations count subsets. If order matters, use permutations. If order does not matter, use combinations. And the reason combinations have the extra r factorial in the denominator is because each unique subset of r items can be arranged r factorial different ways. Since combinations don't care about these arrangements, we divide by the r factorial to count each subset only once. We essentially just deduplicate to get our unique count of subsets. If you found this video helpful, consider subscribing, commenting, or liking the video to support the channel. I'm Joe, and thanks for spending some time with me.